Welcome learners. In today's lecture, we are going to continue our discussion with the semiconductor diode, and we are going to look what happens when a diode is placed inside a circuit, especially when it is applied with different voltage sources that can be either a DC source or an AC source, and see its effect in terms of its various resistance level. So in today's lecture, we are going to first understand the diode's operation in terms of various resistance levels, and later on we are going to see how we can map a diode's equivalent model in case we want to utilize its characteristics using basic RLC circuit elements. So let us begin our discussion first with the resistance levels. So we are going to study three different resistance levels when working with diode in any given electric circuit. The first resistance will be DC, or we call it as a static resistance. The second resistance is obviously going to be the AC resistance or dynamic resistance. And the third resistance is going to be called as averaged AC resistance. So again, these three different resistances are associated whenever we apply source, which can be a DC voltage source or it can be an AC voltage source. For the DC voltage source, the first type of resistance is going to be analyzed, and for the AC source, the last two are going to be analyzed. So how we are going to do the analysis is dependent upon the behavior of the diode. So in the previous lecture, we talked about something known as a characteristic curve. So characteristic curves are basically associated with any electronic device to understand the behavior of that electronic device. Since we are talking about the semiconductor diode, so we saw this behavior of the diode in terms of its characteristic impedance or the characteristic curve. So it had a current on the vertical axis and the applied voltage on the horizontal axis with negative and negative voltage over here. So we saw that if we are using an practical diode, it is always going to have a behavior as such. So the current is going to start from here and it is going to have certain resistance. After some time, when it crosses its knee voltage, it is going to have a maximum value, and later on it reaches its saturated value of the current. This point over here we termed as the knee voltage. For silicon, its value was 0.7 volts, and if we are using germanium, its value is normally 0.3 volts at this stage. So this is for silicon 0.7 and germanium for 0.3, and on the opposite side we have a very small amount of current, normally in microamps. So this is the practical behavior of the semiconductor diode, which we termed as its characteristic curve. Now, keeping with this characteristic curve, we are going to work on figuring out the various resistance level, and whenever we draw this characteristic curve, we talk about something which is known as a Q point, which is basically an intersecting point between the value of current and voltage, which we term as IDQ for the current at the Q sequent point, and this can be VDQ, voltage at the intersection for the Q point, where this Q point is known as quiescent point. Quiescent means something that is still or which is not changing, still or unvarying. So this is what is meant by a Q point. So once we figure out where the Q point is appearing due to the applied voltage, we can say what is going to be the resistance level for the diode in any given circuit. So if we talk about the first type of the diode resistance, which is the DC resistance, we can find its resistance using the known or famous Ohm's law equation, where the resistance R capital of D is the ratio of VD over ID. Keep in mind that I'm using capital alphabets for resistor voltage and current, and if we are basically considering the Q point, then the equation will have VdQ and IdQ as well. So the point where this intersection happens is basically called the Q point, and from this Q point we can find the resistance. Obviously our point of concern will be in the forward bias condition when the diode is conducting and we are generating or getting a certain output from its behavior. In the reverse bias condition, we know that the current is going to be very low as seen from here. So the current is going to be a low value, but the resistance is going to be very high. And in the forward bias condition, we can find the current using this mathematical expression with already known resistance and current's value, and the current is obviously figured out using the Q point that we have seen. So to better understand this, let us have a look at an example question and see how can we find the resistance level, specifically the DC resistance level for any given diode in a circuit. So in this example taken from our textbook, we are asked to find the DC resistance level for the diode, which is having the characteristics shown in this figure 1.24. In the first part, we have been asked to find the resistance if the current is at a lower level of 2 milliamps. So this is the current. In the second part, we need to find the current if we need to find the resistance if the current is at a higher level, which is at 20 milliamps. And in the third part, we have been told that the voltage is now a negative value of minus 10 volts, which means it is in the reverse bias condition. So now what is going to be the resistance? So if we solve for these parts separately, let's say for the first part, we need to find the resistance R of D. So we can use the Ohm's law, which is the ratio of the voltage provided and the current which is given to us. So if we have the value of 2 milliamps for the current, we can find that the intersecting point or the Q point, which is shown over here, this is our Q point, is having the voltage of 0.5 volts. So it comes out to be 250 ohms. So this is the resistance that we are going to get when a DC voltage source is applied to the diode, keeping in mind that this Q point is also going to be at a static point. It is not going to vary or move along this characteristic curve shown over here. So it is going to be a static point over here because the applied voltage is a DC source. So for the first part, the resistance comes out to be 250 ohm, and we can see that it is at a higher level. Now let us solve for the second part. Again, the resistance is the ratio of voltage to current. So since the current now is 20 milliamps, so its equivalent voltage, and this is the stable Q point, so let us say this is Q2, the voltage comes out to be 0.8 volts, and thus we get the value of 40 ohm, and we can see the resistance is now getting decreased compared to the previous value of 250 ohm. So what we can do the analysis from this results and with respect to the graph is that as long as we are less than the knee voltage, so the knee voltage is obviously going to be some point over here. If we are assuming that we are using silicon, so the knee voltage is 0.7 volt. This is the point where the diode starts to conduct the current. So if the value of voltage is less than the knee voltage, we see that the value of resistance is high, so the current value will be less, and as soon as the voltage crosses the knee voltage, the value of current is getting increased, and thus the resistance is getting decreased over here. So the resistance is getting decreased, the current is getting more, and hence we can verify this from the results and the graph as well. For the final part, we have been given that the voltage is in the negative 10 volts. So again, the resistance in this case is the minus Vd by Rd. Normally we don't want to change the equation, so it is going to be minus 10 volts. Current is obviously very low in the reverse bias condition. We already read about the reverse saturation current, which happens when we are using the reverse bias condition of the diode. So this is that current, and it comes out to be nothing but just 10 mega ohm. So you can see the resistance has increased a lot in the reverse bias region. We ideally said that it becomes infinite, or it is a very higher value, and it can be seen over here. So in terms of resistance, if we just compare all these three results from all the parts, we can see the resistance of part C is very high, and then the next in line is the second part, which is A, and then finally we have resistance which is the lowest, it is of 40 ohms. So 10 mega ohm is greater than 250 ohm, which is greater than the 40 ohm. So this is what we got, and we mathematically verified this and graphically also understood that if we are in the reverse bias resistance region, the resistance is very high. Then we move towards the forward bias. So again, this region over here less than 0 is our reverse bias region, and if we move in the positive direction, so this region over here is our forward bias region. And we can see even in the forward bias region we have two categories. If the voltage is less than the knee voltage, then the current, the resistance is high, the current is low, as shown over here as 250 ohm. And if we cross the knee voltage, the resistance becomes less and the current is increased, as shown over here. So this was all about the first type of resistance when dealing with diodes, and this was the static or DC resistance. Now let us move to the second part or second kind of resistance, and that is known as the AC resistance. So we say the second kind of resistance is AC or dynamic resistance. So we say this is a dynamic resistance. So by dynamic resistance, what we mean is that the applied source is an AC signal. So again, what we are having as a input is a sinusoid signal. So this is our input signal. It is going to have some positive value, a positive thrust, and a negative value. So we can identify is at positive and negative input voltage. So now the input signal is an AC signal compared to the first case where the input signal was a DC value, or V out was a DC value. So now what is going to happen with the AC signal? So in terms of the AC signal, we have to again look into our Q point. So we know that the Q point, ideally, if we draw the current and voltage characteristic curve, so the Q point is going to appear over here. Let's say we have this Q point, which is just the intersection of the IDQ and VDQ. So this is our IDQ and this is our VDQ. So this is our Q point. Now when an AC signal is applied, the Q point will not remain at a stable or static position, rather it is going to move in a to and fro motion. So Q point might come is existing over here. After some time it can move upward or it can come to a lower value. So this is happening because the input signal is getting changed. When we have a higher peak, the Q point moves to a higher value. Again, if we come to a lower value, the Q point comes back to its initial position, and then if we go to the negative cycle, the Q point comes to its lowest value. So that's why it becomes difficult for us to find the exact location of the Q point. And if we don't know the exact location of the Q point, we might not be able to know that what is the maximum amount of current or the minimum amount of resistance available. So in order to understand this better in terms of the AC resistance, let us see what happens to the characteristic curve and how this Q point is moving. So let me draw this characteristic curve again, and let us figure out how we can find the Q point, or how the Q point is moving between the voltage and current graph. So let us say this is our curve and this is the graph that we are having. So initially the Q point was over here. Now what happened? So our Q point, our Q point, because of the AC signal, first jumped to this point. Let me call this Q1. After the negative cycle was received, the Q point came back to the second point. Let us call this Q2. The same Q point is basically moving in an upward and downward trend, or it is doing a to and fro motion from its base point, which was Q0. So if we try to map this in terms of a sinusoid, we can say that these are the points where the Q point is basically hovering or moving to and fro. So this is the initial point, and the remaining are basically the maximum or minimum values. So if I try to draw this such that my point comes out to be, or my sinusoid is going to be something like this for the current value. So this is the sinusoid with the maximum value of current over here, minimum value of current is over here, and this is the, so this region is basically the change of current in terms of the Q point. Similarly, I can draw this in terms of the change of voltage. So if this is my signal, I can draw it like this. This is for my voltage. So here the voltage is also getting changed from maximum point to a minimum point. So this is my sinusoid. So what is happening if the initial value of the Q point was at rest? So I can see that the initial Q point was over here, when this is the intersection between the current and this is for the voltage. As soon as the current reach its maximum point over here, we can see the maximum point of voltage is also reached over here. Thus the Q point jumped to this point over here. Then when the cycle again reached to 0 point, the Q point retracted from Q1 again to Q, and we can see the current and the voltage also came back to its resting position. Then at the negative cycle, the current reached its lower point, the Q point moved from Q0 to Q2 over here, and the lowest point is also reached for the current and the voltage. So this is how the Q point is moving between minimum and maximum values with regards to its ID and VD values. So since the Q point is getting varied, it becomes difficult for us to find the exact location of the Q point. Why? Because when the value of voltage is increased, the current also gets increased and the Q point is also getting increased. So Q is moving up and down with the increase or decrease of the voltage and current. So in order to find the approximate value of this Q point, what we do is we again look into our curve. So we take our curve. So let us draw our curve like this, and we know that this was our Q point, the center Q point, and it is going to move up or down. So let us say the Q point might come over here or it might go over here. This was our Q1 and this was our Q2. So in order to find the exact location, we use the geometric analysis and we draw a tangential line that covers all these points. So this is a tangential line. So now once we have this tangential drawn, we can just complete the Pythagoras triangle, and thus we know that now the horizontal axis is the change of the voltages and the vertical is the change of this current over here. So with the help of this tangential line, the line which is just touching the curve and all the three Q points, we have come up with a solution that can give us the average of these values. Thus to calculate the average resistance, we use this mathematical expression: small r of d is equal to the change in voltage of the diode or to the change of current of the diode. So this is the mathematical expression that we are going to use to find the AC resistance of a diode or the dynamic resistance. So this is the first equation that we can utilize to find. And most of our examples, we can use another form of equation which is known as the approximate equation, that is also acceptable in finding the average or the AC resistance of the system, and that is represented as 26 millivolts divided by the current of the diode. Again, keep in mind I have used a capital ID in this case. So this is the second equation or the approximate equation that we can also use to find the AC resistance of the diode. So let us see how did we translate from equation 1 into equation 2 and why we are saying that it is an approximate equation. So in order to understand this conversion, we basically look into some mathematical proofs. So let us say, how did we reach to this equation? So I'll use this space. So we know that the characteristics of diode is mathematically represented by the Shockley's equation. So the Shockley's equation is basically helping us in understand how the diode works, which means how can we find the currents associated with the diodes or produced by the diode. So Shockley equation is that the forward bias current is equal to the reverse saturation current and the factor of exponential with the forward bias voltage, the room temperature, nVt by dt minus 1. So this is what we know from the Shockley's equation. We can also write this equation in its complete form as is e raised to power Vd divided by nVt minus I of s. So let us say this is our equation 1, or this is the complete form of the equation. Now in order to proceed further, let us differentiate this equation, because since we want to find the resistance, which is the ratio of the voltage to current, let us differentiate this equation with respect to Vd. So if we do so, our equation will become Id divided by Vd, and it is d by dVd, and we differentiate it on the other side. So we know that Is is a constant, so we can move it outside. Then we will have dVd, and this will going to be E V of d divided by nVt minus d dVd I of s. So we differentiated the first equation to basically figure out what is going to be the resistance value. Now we know that Is is a constant, so this will automatically become equal to 0, and as per the differentiation rule. So we will be left with dId by dVd equals to Is d divided by dVd e raised to power Vd divided by nVt. Now we apply the differentiation rule on the exponential. So the rule says if we have d by dx e raised to power a of x, so we can get output as a e raised to power a of x. So the same thing is applied over here. So we can get, so let me use the space over here. So we can get the output as dId by dVdt is equal to, so Is will remain as it is, as this is a constant. Exponential will remain with its value, which is Vd, or with its power nVt, and then the thing that the exponential has is a, which is going to be outside for us, which is going to be divided by nVt. So this is what we get after differentiation of this equation. Now if we further look into this equation, we can write this equation in this form: 1 divided by nVt, and I have Is e raised to power Vd by nVt. Now this portion over here from equation number 1, this portion over here from equation number 1 is nothing but the sum of Id plus Is. So I can write this as 1 divided by nVt, and this becomes Id plus Is. So I have utilized equation 1 and replaced the numerator with its equivalent. And since we know that the forward bias current is always greater than the saturation current, so we can neglect I of s. Thus our equation then comes out to be Id divided by eta Vt. So this is what we have now. Now since we need to find the resistance, we are going to flip this complete equation upside down. So this comes out to be eta Vt divided by Id, and this equation over here, this Veta value, is basically nothing but the room temperature which we saw in the Shockley's equation. This is the point which we saw, and we know that with the values that it has, so the final output comes out to be 26 millivolts divided by Id, and this is the proof of our equation where the value of eta is taken as 1. So hence we have proved our equation, or the approximate equation, that is equation number 2, that we can also find the AC resistance or the dynamic resistance of our diode using this approximate equation, which comes from mathematical proof. So again we have the liberty of utilizing both sets of equation. So now let us look at an example and see that how can we use these two equations to find the unknowns. So in this example we have been given, so let me zoom in so we can see the example clearly. So in this example we have been asked to find the AC resistance of the system In the first case, when the current is located at a low value of 2 milliamps. In the second case, if the current is at a higher value of 25 milliamps. And also in the third part, it is saying, see what is the comparison if we had a DC source rather than the AC source. So in order to find the AC resistance, in this example, we have used the equation RD is equal to the rate of change of the voltage and the rate of change of the current. So this is VD by RD. This is the first equation that we have seen, and it has been utilized over here. So what is happening when we take the current at 2 milliamps? So we draw a on the characteristic curve, which is the blue line which will be provided to us, the first step will be we'll draw a tangential line as shown over here. With the tangential line drawn, we can see that the minimum and maximum value of current on the vertical axis is at 4 milli and at 0. So the value of current or delta ID is the difference of higher minus lower current, which comes out to be 4 milliamps. Similarly, if we draw the vertical lines towards the voltage, so we found that the difference in voltage is 0.76 minus 0.65. So these are the lines that we have. So the voltage comes out to be 0.11. Thus, the resistance over here is basically the ratio of 0.11 by 4 and comes out to be 27.5 ohm. Similarly, for the second part B, if we now take the current at 25 millivolts, the step is to draw a tangential line as close to it as possible. So this is the tangential line that has been drawn. From here we can see that the current is having a maximum value of 30 and minimum value of 20. So this is delta ID. So delta ID comes out to be 10. And if we extend these lines towards the voltage, we can see the voltage is at 0.8 and 0.78, and it comes out to be 0.02 volts. So the average the AC resistance comes out to be 2 ohms for this case. In the third part, we have been asked what happens if we take the same characteristic curve graph and find the DC analysis or DC resistance. So that is very simple. We use these equations for the current at 2 milliamps and the same equation when the current is at 25 milliamps. And we can see that at 2 milliamps, the exact value comes out to be 0.7 for the voltage. So here the resistance is 350 ohm. And at 25 milliamps, the exact value comes out to be 0.79. So it is at 31.62 ohm. So this is how we can find the AC resistance of the signal or any characteristic curve provided. Now, how about if we use the second method or the approximate equation and do the numerical again? So let us use the approximate method or the equation of the approximate and find the AC resistance, which means we are going to use this equation over here. So the equation is we need to find the AC resistance using this mathematical expression, which is 26 millivolts divided by capital ID, where ID is the current coming from the DC analysis of it. So if you want to find this, we know that for the first part ID is 2 milliamps. So we just put the value of 26 millivolts divided by 2 milliamps, and the answer comes out to be 30 ohm. Okay, so now we can see that it is not exactly equal to what we found in the example using the first equation, which was this. So in our first case, the resistance was 27.5 ohms, and if any equation is approximate, its values should be near or closer to it. So how can we bring it closer? So keep in mind, another important factor is the value of eta, which we in the Shockley equation is known as the ideality factor. So normally we discuss that this ideality factor is provided by the vendor and its value is between 1 and 2, but normally we take either value 1 or 2. So now whenever we have a value of current that corresponds to a lower value or something that has a value less than the knee voltage, so we take the value of eta to be 2. What it means is, if we look at the 2 milliamp current, it's a lower value and its corresponding voltage is 0.7. So whenever the value of current ID is less than the knee voltage here being 0.7 volt, so we are always going to multiply our answer, which was 13 in this case, using the approximate equation. We are going to multiply it by 2. Once we do this, our answer comes out to be 26 ohm. And now if we compare the approximate answer to the answer which we got from this equation, it is almost near. So the answer we got with the first equation was 27.5. Here we got close answer which is 26 ohm, or the approximate answer. So always keep in mind, if we have a current value which is having a voltage lower than the knee voltage, then we always going to multiply our answer with value of eta equals to 2. Now let us look at the second current, or part B. In part B, the value of current ID is 25 milliamps. It's a higher current value and its corresponding voltage was around 0.78. So it is higher than the knee current value. So here the value of ID, or the voltage which is corresponded or available at ID, is having a value of greater than knee voltage. So in this case, if we directly apply the equation, which is 26 millivolts divided by 25 milliamps, we get the answer of 1.4 ohm, and this is almost close to the 2 ohm which we got from our previous value. Second thing associated is that why we are using this value of ideality factor to be 2, and in this case, in the second case, when the value of the current was 1, the ideality factor is normally taken as 1. At the output we just multiply it with 1, hence we get the same 1.4. So this is basically due to something known as the body resistance. So this value basically comes from the manufacturer due to the body resistance known as RB. So this body resistance is basically coming from the resistance of the physical diode that is constructed at the vendor or inside the factory. So this RB is basically having the value of, or is giving the value of eta to be 2 or 1, and hence we get these results. So to summarize, whenever we are using approximate equation to find the AC resistance of the system, you have to multiply your answer with the value of eta. That can be value of 1 or value of 2. You are always going to multiply the eta having a value of 1 if the value of current, let's say the value of current is 25, the voltage is higher than the knee voltage, then the output will be multiplied with 1. If your current is having a value less than the knee voltage, then you are going to multiply your output with 2, as we saw over here. So this is how to use the approximate equation to find the AC resistance of the semiconductor diode. So now finally let us come to the third kind of resistance, and that is the average AC resistance. So the average AC resistance is basically your third kind of resistance that is shown over here. So let me remove this. Okay. So in the average AC resistance, what is the difference and why do we use it if we already have an AC resistance? So average AC resistance basically is used when the input becomes very large. So this kind of resistance is used when the input is a very large value. So what does it mean? So let us look at the characteristic curve of the diode. Again, we have voltage on the horizontal axis and current on the vertical axis. Now if we look at the input, we know for silicon the knee voltage is at 0.7. So but if you look at the graph, the current is basically not immediately rising at the knee voltage, rather it is risen before that period. So if you look at the curve, the input is taking longer, it is having a larger swing. So before the knee voltage, the current increased, and after some time it crossed the knee voltage at this point, and then it became flat, or it is moving towards a saturation value. So when this kind of scenario happens, we say that there is a larger swing, or it's a broader swing that is happening. And when this kind of broader swing happens, we say that we had a larger input, and thus the analysis now is in the domain of the average AC. If you compare this to the AC, you can see over here, if I get rid of these graphs, we can see here that for the AC resistance, the characteristic curve immediately increased after the knee voltage, and thus it moves, where the knee voltage value was 0.7 for the silicon material. But in the average AC, the input was a very broader swing, because the current increased before the knee voltage appeared, and then after some input or some time it reach the knee voltage value of 0.7. So this is the broader swing which moves our analysis from the AC to an average AC. And thus in the average AC the analysis becomes very easy. Rather drawing the tangential line, we just take the difference of the maximum and the minimum values for the voltages and currents. Our equation remains the same. So the average AC will be the difference of the voltages to the ratio of the difference of the current, but this time we are considering point to point. So what it means is, if we want to find the average resistance, we are going to take the minimum and maximum value for the voltages and current. For example, if we want to find the average resistance over here, we can see that for the tangential line drawn, the maximum value of current is 15 and the minimum value comes out to be 2 milliamps over here. So this is the difference, which is 15 milliamps. And for the same set of currents, the corresponding voltages is at 7.725 and 0.65. This means that for 17 milliamps, the voltage is 0.725, and for 2 milliamps, it is around 0.65, and this is the difference of voltage. So the average AC resistance comes out to be 5 ohm. So this is the average AC resistance that we normally use for the analysis of the semiconductor diode. Now let us come to the second portion of our discussion in this lecture, and that is about the characteristics of diode, and that is that how can we use diode if we don't have the physical equipment available. So let's talk about something known as equivalent circuits. So what are equivalent circuits and why they are needed in the first place? So let us say you are performing a certain experiment and you run out of semiconductor diodes. What does it mean? That you don't have enough physically available semiconductor diodes. So now what's the solution? So the solution comes in the form of equivalent circuits. The equivalent circuits are basically a combination. So if I try to define it, an equivalent circuit is basically a combination of basic circuit elements. So basic circuit elements, our basic circuit elements being resistor, inductor and capacitor. Also we have voltage and current sources. There are 5 in total, but let's say that the sources are always there. So we use these basic circuit elements properly chosen. So these basic circuit elements are properly chosen that best represent the actual characteristics of our device. Actual characteristics of our electronic device. In this case, our electronic device being the semiconductor diode. So this is the diode. So what does it mean? So for example, if we have a circuit and we say that we have a DC voltage source and we have a resistor, we had a capacitor, and then we had our diode, and then we have any load over here, and thus this is what we are using. So we have a resistor, capacitor, a silicon based diode, and at the load we have a capacitor. Now let us say in this circuit our diode gets burned, or we want to replace this diode. So what's the best way to do it? So we can replace this diode in our circuit with its equivalent model. So let us say we have the same circuit with a resistor and a capacitor, but now we have replaced this with its equivalent model, and that equivalent model can be something like this. So now we can have V of k and average RC. So this is basically what is happening. So equivalent circuit models are needed when we have shortage of diodes, or we don't want to use a diode, or for any reason that we are unable to use the diode. So we replace it with its basic circuit elements that can be resistor, inductor and capacitor, and thus we can go on with performing our experiments. Although the behavior will be not exactly matched, but it is going to be the best representation of our device. So this is how the circuit or equivalent circuit models are, and this is how we utilize them. So for the diode, there are 3 basic equivalent circuit model technique that we can use. The first one is called the piecewise linear, the second one is called the simplified or the approximate model. Some of the books use the approximate, and the third one is known as the ideal diode model. So here you can see the various configurations and its output in terms of this characteristic graph. So if you look at the piecewise linear model, how we can replace diode? So if we have a diode in physical symbol is such, and if we are using it in our circuit and you want to replace it in any scenario, whether the diode gets burned or we don't have more of the diodes physically available, so we can replace it with this equivalent model. So the configuration will be, theoretically, our circuit will have V of k followed by a resistor that we can find its average AC resistor, because average AC means that the input signal is obviously a sinusoid. So that's why we have used an average AC. If this is a DC signal, then our resistor will be RD, and then we represent it with an ideal diode symbol. So its behavior will be something like this. So the characteristic curve for the piecewise linear, as the name suggests, why we call it as a piecewise, so we say that this is first piece line segment and this is the second line segment. So this why they are in different pieces. So we say that it's a piecewise and its graph is a linear. That's why the name comes out to be a piecewise linear model. So you can see that the output graph is almost resembling the output characteristic curve of the diode. We know that the output characteristic curve of the actual diode is going to be non-linear. So its behavior will be something like this. But since we are not using the exact diode, we are using its equivalent model. So this is the output which we are going to get, and again it is acceptable to us. And here we can see that when the current or the slope reaches the knee voltage, there is a sudden increase, but it is a linear increase. It is not a curve increase as shown in this original behavior. So this is the characteristic of the curve if we are using the piecewise linear model. If I come back to the model configuration, there is a symbol used over here which resembles a battery, but keep in mind this is not a battery. Here we are just saying that V of k is the amount of forward bias voltage needed for the circuit to operate, and thus we have used a battery symbol. This is not a battery. So this is not any external, not any battery, rather it's just a symbol to know that this is the knee voltage. Thus we have written V of k followed by any average resistor, and then we have an ideal diode. So this is the combination that we can use when doing the theoretical analysis. The second model is known as the simplified and approximate model, and this is the widely used model in our book for analysis, where what is happening is that we get rid of the resistor and thus we just replace it with a knee voltage symbol and an ideal diode, and the output is going to be something like this. So we can see that when the voltage is 0 or it is a very low voltage, and anything below the knee voltage there is no current. As soon as the system reaches to the knee voltage, there is a certain jump in the current, and we can see that it is making a 90-degree angle over here. So this is the behavior of the approximate model. Now why it is making a 90-degree? So it's very simple that whenever we have a slope, we can define it mathematically in terms of its resistance. So the slope is mathematically nothing other than its resistance value. If there is no resistor in the circuit, as we see over here, which means that the resistor is 0, so our slope is basically having no resistance, and thus the slope value comes out to be infinity, and if we find the angle of infinity, it comes out to be 90-degree. Thus we can see that the slope over here shown is having a 90-degree angle with the base. And this is basically the behavior when we use an approximate or simplified model. Again, you have to keep in mind how the model is going to appear in the circuit and what is going to be the output as shown as the characteristic curve. Finally, ideal model is something that we have talked about before when we compare diode with a switch. Whenever we are using an ideal model, we have to keep in mind that its behavior is going to be such. And when we have an ideal model, the system behaves as a short circuit, which means that the voltage is going to be 0, but the current is going to be having certain value. So we can see in the graph shown over here that as soon as we have an ideal model, even at 0 voltage, we get the value of current that can be the maximum available inside the circuit. So the diode, to summarize, we have diodes equivalent models or equivalent circuits. There are 3. The first one is called the piecewise linear, where we use this kind of a configuration. in our circuit, its behavior is going to be a linear slope, a piecewise linear. Again, the slope is figured out by this resistance. You should know this about the graphs in your geometry courses. That is just tangent theta is the ratio of perpendicular by base, and thus we get this linear slope. And then we use the simplified model where we don't have the resistance, we just have the battery notation. It is not an external battery, it is just representing the forward bias condition or the knee voltage followed by an ideal diode, and its behavior will be a sudden increase in voltage after the system has reached the knee voltage value of Vk. And ideal, we have already seen that at 0 voltage we are going to get some current from the system. So this is the diode equivalent circuit models, and in our analysis most of the questions are related to second and third kind of diodes, either the approximate model or the ideal model. Finally, we go towards the last topic, and that is basically talking about the reverse recovery time. So reverse recovery time is basically associated whenever you are reading with the whenever you purchase any electronic device, you get something associated with it, and that is known as data sheet. So data sheet basically tells you how much voltage is needed for any electronic device to operate, what is the maximum output that it is going to generate, what are the resistance levels, what is the behavior of the system. So one of the entity associated with diodes is the reverse recovery time. So reverse recovery time concept, or the main idea behind this is, main idea is what happens when our system is working in the forward bias condition and we immediately switch it to the reverse bias condition, or it can be vice versa. So normally we don't operate in the reverse bias and switch it to the forward bias, but the idea is what happens if our system is working in the forward bias condition, which means that our current is getting generated, we have a knee voltage, there is less resistance, and immediately we change the polarities of the diode. So in the forward bias, this is the polarity, the current is moving, we have applied a certain voltage, and immediately if the system is behaving and you change the polarities as such, now you change it from the forward bias to reverse bias, then what is going to happen? So that is basically analyzed in terms of the reverse recovery time. So the graph over here is basically again the characteristic curve with the, but here we are just looking at the current's behavior with respect to time. Now let us say our system is working in the forward bias condition and we are getting certain current over here, and we know that what is going to happen is at time t1 we do the flip, we basically change the switch from forward bias to reverse bias, which means we have changed the polarity as shown over here for the diode. Now ideally we have seen that the diode is change its working from the forward bias, so it means that whenever the current was produced, immediately it is going to come at 0 value of current, which means in the reverse bias the system becomes open circuit and no current is going to fall, which means if the diode was in the forward bias working as a short circuit, when we flip the switch at T1 it will become an open circuit and the current is not going to pass. Here the current should be equal to 0 amps, and here in the current was something value greater than 0 amps. This is what we have seen, but practically this is not going to happen instantaneously, rather it is going to take some time. So what is going to happen is that if we switch at T1, the system is going to realize that the current value is not going to change and it is moving from forward to reverse bias, which means the current will first start to lose its value from positive to negative, and then it is going to come back to its ideal stage, and this is known as the storage period T of S. After a certain time, the storage period is going to move into a transition stage where any negative value of current, let's say minus 5 amps or milliamps, is going to become from minus 5 and move towards its lowest value, which is 0 amps. So this period is known as the transition period. So overall reverse recovery time is basically the sum of the storage period where the current gets from a higher value, let's say from 5 milliamps, and it comes back to minus 5 milliamps. So this is the time where the current is going to come back to its lower value, and then it is going to store this data -5 amps, and after some time it is going to move from -5 back to its basic value of 0 amps in the transition state. So the reverse recovery time basically tells you that it's the product of the storage versus the transition period, and in reality diodes need this time to basically to convert from one domain or from one biasing region to the other biasing region. So this is normally a certain value that is provided in the data sheet, and the idea was just to tell you that what happens if you immediately change the polarity at the output. If you are measuring it with a DMM, you are not going to get the immediate current, rather it is going to have some values that will be the reverse recovery time associated with it. So this was a small topic on reverse recovery time based on the data sheet provided, and that's all for today's lecture. See you in the next lecture.